Respected sir or ma'am, this is Srinavya bearing the roll number 24951A05CE. I am from CSC Department F section and currently pursuing second semester. Today I am going to speak on the topic Introduction to Linear Waves from the course Differential Equations and Vector Calculus. Let us now get into the topic. Introduction of Linear Waves. Introduction to linear waves. Linear waves are disturbances that propagate through a medium without changing their shape. These waves are characterized by a linear relationship between the displacement and restoring force. Common examples include sound waves in air and waves on a string. Here's a well-structured speech on linear waves focusing on concepts from differential equations and vector calculus that is ideal for technical seminar or academic presentation. Today, I want to take you into the fascinating world of linear waves, a fundamental concept in physics as well as in engineering, and explore how they are described and analyzed using the tools of differential equations and vector calculus. The question arises, what are linear waves? A wave is a disturbance that travels through space and time, often transferring energy. When a wave follows superposition principles, meaning multiple waves can add up together linearly, we call it a linear wave. Examples include vibrations on a string, sound waves in air, light waves in vacuum, in linear approximation, and small water waves. But how do we mathematically model these waves? Coming to the characteristics of linear waves can be described by their amplitude, wavelength, frequency, and speed. The amplitude is the maximum displacement from the equilibrium position. Wavelength is the distance between consecutive points in phase, such as crest to crest. The wave equation, a partial differential equation. At the core of our discussion is the linear wave equation, which is one dimension, that is written as dou square u by dou t square is equals to c square dou square u by dou x square. Here, u of x comma t is the wave function, that is displacement, pressure, etc. C is the speed of the wave and dou represents partial derivatives. The equation describes how a wave propagates through a medium with time and space. To derive this, we use Newton's laws applied to a small segment of string or air parcel, and resulting force balance leads to this second order partial differential equation. Coming to the types of linear waves can be classified into two main types. The first is the transverse waves and the second is the longitudinal waves. Transverse waves involve oscillations perpendicular to the direction of wave propagation. Longitudinal waves involve oscillations parallel to the direction of wave propagation. Coming to the wave equation is fundamental relationship that describes wave propagation in a medium. In one dimension, it can be expressed as dou u square by dou t square is equals to v square into dou square u by dou x square. Here, u represents the wave function, t is the time, x is the position, and v is the wave speed. Coming to the superposition principle. First of all, what is superposition principle? The superposition principle states that when two or more waves overlap, the resultant wave is the sum of the two individual waves. This principle is the key to understanding phenomena such as interference and diffraction. Linear waves maintain their individual characteristics even when they overlap. The general solution to the 1D wave equation is u of x comma t is equals to f of x minus ct plus g of x plus ct. This represents two waves, one moving to the right at speed c and one moving to the left at speed c. This is where linearity becomes important. Because the equation is linear, the sum of solutions is also a solution. This allows for superposition where multiple waves pass through each other without interaction. Let us know more about the wave interference. The interference occurs when two or more waves combine to form a new wave pattern. Constructive interference happens when waves add together, resulting in a larger amplitude. Destructive interference occurs when waves cancel each other out, resulting in lower amplitude. Let us now know about dispersion of waves. Dispersion refers to the phenomena where wave speed varies with frequency. In linear waves, different wavelengths can travel at different speeds in a medium. This can lead to spreading out of a wave packet over time. Coming to the vector calculus in higher dimensions, in real world problems, waves are not one dimensional. Think of ripples on a pond or seismic waves through Earth's crust. In 3D, the wave equation becomes dou square u by dou t square is equals to c square delta square u. Here, delta square is Laplacian, a key operator in vector calculus, defined as delta square u is equals to dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. The Laplacian measures the spatial curvature of the wave and helps us understand how disturbances spread in a medium. Vector calculus also gives us tools like gradient, which is delta u, the points in direction of steepest increase, divergence, which is dou into f, that measures how much a vector field spreads out, and curl, which is dou into f, that measures rotation or swirling of vector fields. These are all essential in analyzing electromagnetic waves, fluid waves, and also acoustic waves. Coming to the applications of linear waves, linear wave theory is applied in various fields such as acoustics, optics, and engineering. Understanding sound waves helps in designing better audio systems and noise control. In optics, linear wave concepts are crucial for study of light propagation as well as lens design. Understanding linear waves has vast implications. The first one is engineering, where design of bridges and buildings to withstand vibrations include the usage of applications of linear waves and signal transmission through wires and fiber optics. The second one is in physics, where in quantum wave functions and light and sound behavior, the linear waves are utilized. The third one would be in medicine, in ultrasound imaging, ECG and EEG wave analysis. The fourth one is geophysics, that is its usage in earthquake wave modeling. All of these rely on accurate modeling using differential equations and vector calculus. Coming to the mathematical modeling of linear waves, the mathematical models for linear waves often involve differential equations. These models can predict wave behavior under various conditions and constraints. The numerical methods are frequently used to solve complex wave equations in practical applications. Here a question arises: why this is a complex engineering problem? Though wave function appears elegant, the complexity lies in solving it for real world geometries, handling inhomogeneous media where wave speed c varies, dealing with non-ideal boundary conditions, applying numerical methods like finite element analysis where analytical solutions fail. These turn a clean mathematical equation into a real world engineering problem. Now let us know about the boundary conditions and real systems. Solving the wave equation isn't enough. We need initial as well as the boundary conditions. Here, what was the initial shape of the wave, and is a medium infinite, or there are boundaries like Walser strings? Depending on these two questions, we get solutions involving standing waves, reflected waves, or even resonance phenomena. Let us get into the conclusion. Linear waves are essential for understanding wide range of physical phenomena. These principles of linear wave behavior have significant implications in science as well as in technology. A solid grasp of linear wave concepts is fundamental and foundational for further study in physics and engineering. Coming to the final conclusion, to conclude, linear waves are at the heart of many natural and engineered systems. The wave equation born from differential equations and shaped by vector calculus provides a powerful model to predict and understand these phenomena. Whether you are an engineer designing a noise cancelling headphone or a physicist studying gravitational waves, the principles of linear wave theory are both fundamental and far reaching. Mastering them is the key to solving some of the most important problems in science as well as in technology. Thank you.